Good morning, how are you all? What a lovely quiet class I've got. They just won't do. My classes are never quiet. They should be very nice and noisy and lively. Anybody in my class before? One? Two? Well, welcome back. Well, this is STAT2402, second year stats. The title is Analysis of Observations, which is rather a bad title because it means nothing at all. All data is observed in somewhere or other, right? So a better title is going to be Analysis of Discrete Data, and we'll see that as we go through. How was the first week? Did you miss me? Oh, did it? Just need a letter, that's all. All right, lots of stuff in the first week. Who here has done Stats 1400 last semester or some of the time? One, two. You did it 2 years ago, right, with me? 2021 with me, right. So Stats 1400 last semester, right? Who has not done any R before? Great, wonderful. Okay, so the others have done some R before. R is a massive package. The reason is it's actually free open source, which means people just keep adding to it. It's great in one way, but of course it just means it's massive. It just keeps growing and bigger and bigger. Now the lucky thing is that nobody knows all of R. It's impossible, I suppose. It just keeps growing. So don't be afraid you don't know a lot of R yet. But you will learn as you go through. You know, I do stuff and I keep looking it up all the time. All of us do it, right? You know, once you get some ideas of how things work, you don't have to clutter your head with all that information. You know how it works. You can look it up. The other thing is all your assessments are open book. All your assessments are open internet. All your assessments are take home. You can do it in your time, at your home, with a cup of coffee, whatever else you need. The only thing you can't do is ask somebody else. Now, who will check that? You will check that. Yeah? You will check that. You do stuff, you learn stuff. No point asking others to do stuff for you because that ain't how life works, yeah? Ain't how life works. You can't keep hiding behind your problems because they will keep coming up behind, you know, always. You know, people who avoid problems throughout their lives find they all come and attack you together at some point or other. You just can't avoid them. They find you. So face up to them as fast as possible, right? And you'll make progress much faster. So the thing to do is work through those notes carefully, but know where things are and get some ideas of how to find things. For example, one thing we commonly do is we have a categorical variable, which I've got as 1 and 0. But 1 means male and 0 means female. 1, 0 makes no sense. I want to convert them to male, female. So you go R, categorical variables, relabel, for example. It'll tell you how to do it. Copy the code, paste it, modify it, you're done. Simple, right? That's how it works. But the more you use it, the more practice you get, the better you get at this. Some of the questions in the lecture notes itself and some of the questions in the lab this week are not easy. They're not easy at all. But that's the whole point, right? You just can't keep doing easy stuff to learn stuff. You need to start doing harder stuff. So you get some facility in R. If you're going to be at least anyway, a statistician, a data analyst, or a data scientist, you need R. No two ways about it. You can maybe wrangle your way through Python or whatever else. People use MATLAB, all other kinds of stuff. But to do things properly and be really at the top of your game, you need R. Yeah? So the sooner you start using it and getting used to it, the better you'll get the thing. But as I say, you know, none of us knows all of R. I don't claim to be an expert myself. I'm learning all the time. I keep picking things all the time. I keep using my old R code all the time. I keep looking stuff up all the time. All of us do that, right? But that's okay. As long as you know how things work, you can find them, you can make them work. That's the whole thing. Now, so all the labs will be very strongly R-based, and you'll be using R throughout the course. So as I said again, look at those lecture notes that I have put online, work through them, at least work through them once, have a good look at them to understand how things work, where things are. Get some ideas. There's lots of things in there. And the other good thing, of course, with R is because it's open source, all the stuff you need is online. If you go to online, you'll find whole tutorials online on R, lecture notes online, YouTube videos online. anything you need to learn is going to be there. Yeah, so get used to finding stuff online and get used to actually using the stuff online. Don't go Excel, use R. Excel is cheap and nasty and useless at statistics. Yeah, it's okay to organize data. You can still enter data into that, and that's fine. You can do the thing into R from there. But don't start even finding means and graphs and things. Excel graphs are so bad, so clunky. To control them is just very difficult indeed. R gives you fine control of things, produces fantastic graphs. And as I'll show later on, maybe next week, I'm hopeful, you have lots of synergies with R and other programs. If you haven't used things like R Markdown before, we'll be learning that in this course. There's also things you learn in this course here. I'm hopeful you'll be able to use in your third year and onwards. That's the whole point, preparing you for third year. So R Markdown is one big thing where you can actually have R doing things with R to turn that into a PDF document straight away. From R to PDF, you have a whole report done for yourself. So it's not like Excel or whatever else. You do a graph, you copy, you paste, and 10 days later, I don't like that graph, I want to change that. You have to go back and find out where the data was to start off with. Redo the graph, recopy, repaste. Pain. Whereas R, the data is there, read in straight away in your R file. Modify the thing straight away there, and just run the code again, and out comes a brand new document for you straight away. Right away, right? You come back 2 years later saying, what's going on there? You've still got the R code, you've still got the data there, everything's straight there. Read the thing again, do it again. No problems. Fantastic stuff. We use this all the time, so all the lecture notes you see have been produced through R. They're linked into a program we call LaTeX, which is essentially a mathematical typesetting program. They're linked together, we do the stuff in R, link it up. If I want to change one graph, I do the thing in R. Produce them a document straight away, new, right? Fantastic stuff. So I'm hopeful we'll do all this stuff as we go through there. All right, so I just want to go through quickly the unit unit outline, because while, yes, we've seen this last time. We didn't pay much attention to this last week, so we'll have a good look at this week to make sure you understand what's going on there. So prerequisites, just make sure you understand them. As it says here, you can take some of these as core requisites. If you have any doubts, please come and see me afterwards, or go and see a student services person, and they'll put you right with this. You don't want your enrollment to be all of a sudden invalid in week 4 or 5 or something. So check your enrollment, make sure it's valid, everything is fine. If that's all good, fantastic. If it's not valid, you've got a problem, please see somebody. The lecture notes, I did want to produce the lecture, a unit reader, but because I'm revising the notes this time, I will not be able to keep, I will not have that available straight away. But I'll put lecture notes, as you saw, week by week online, and you can look through those. And I'll pre-record videos. So some of the lecture notes will be coming together beforehand as videos. You should watch them before you come to class. I might not go through all the videos here, I might not cover everything in the lectures itself, but between the recorded lectures and this here and the labs, you'll cover everything you need. So some things I'll let you read by yourself, because I want to cover, I'm not trying to overload you, but I want to cover a bit more than maybe you would have seen in some other courses of the same type, because I think preparing you for the next course is really important. Maybe this is the only stats course you'll do. From here you'll do no more, some students of the class. But I'm hopeful we'll teach you enough to be able to get you interested in this, and maybe you'll, as I say, do a third year with a lot of background. So when you get a third year, one of the things I found in third year, students just don't know R. If you learn the thing here now and do it properly, I think it'll serve you well. The textbook here that we're going to use is this one by Ramsey, which is called The Statistical Sleuth. If you can find a copy in the library, fantastic. I think you will find several copies there that are on very close reserve. But it's a good book to have a look at. You won't, if you don't have a copy, don't worry. All we'll need will be in the lecture notes. So if you can't find a copy, don't worry. If you can find one, it's a fantastic book to have a copy of. We have a 2-hour session, which is Monday 10 to 12. The labs are every week, 2 hours. Make sure you go to the labs or do them or whatever way. Don't take the easy way and do all the labs together in week 5 or 6 or something, or week 12. It just doesn't work that way. You have to learn the thing week by week. You know the assessments come very fast here. I'm not over-assessing. I'm pretty careful how I assess things. So have a good look at that. Learning outcomes, yes, we essentially is going to be analyzing data. The emphasis here is analyzing data and reporting the results, because often the data comes from somebody who knows no stats or very little stats. You can't tell them p-values or this or that. You must tell them what it actually means. What is the whole meaning behind this? And the answers to the questions of interest must be back in terms of the context of the questions. If it's a medical question, it must be in terms of the medical things. Chemistry question, back in terms of chemistry. So as a statistician, you need to know quite a few areas that you're going to work in. You learn these areas as you go through. So, people in our school, for example, our department, work in many areas. I work in medicine myself, I work in biology, chemistry, education as well. Lots of places I work with. You need to pick up the rudiments of the subject. You have to do some of your own research and reading as well as you go through. So as a statistician, you require a large, broad range of knowledge of various fields you can work in. Of course, you might go and specialize in something else, and that's fine. But for the moment, you need to be able to interpret data and see what it means. Detailed outcomes here, you can read them yourself. I'm more interested in the content here. So the first week we've gone past here. Second week we're going to do some more revision of stuff that you should have seen earlier. If you haven't, doesn't matter. We'll do it now. The lab tests, excuse me, are due the Friday of the week. So in week 3, there's one due at 11 p.m. Friday, 13th August. I'm sorry, I can't give the date for that. 13th shouldn't be a problem. Then is week 5 and week 6, a break after that, then week 7, week 9, and week 10. So the idea is each of these lab tests is worth 10%, and what I'll examine in there should be about what it will take you, as if you're doing this in the exam, is a 10% of the exam paper. Maybe a bit more, I suppose. But the idea is you get a data set or so to analyze. You analyze the data set, you give me your R code, you give me your write-up on that, you submit the thing online, we mark it, you get the feedback straight away within a week or so, we hope. It's a large class. It used to be only about 30, 40 previously. Now it's gone to 170 odd, so it may take a while for the tutors to mark it, but they'll mark the thing, and the idea is that you get it back before your next test is due, so you've seen what you've done and how you can improve your work. That's the basic idea. Each of the tests is worth 10%, that's 60%. Your exam is going to be at the end of semester. I have not decided whether it's going to be week 12 or week 13. So week 12 would be the week 12 of the semester, or week 13 is the study break. We can discuss that. But it's going to be a take-home exam. The questions will be there. What you'll get is you'll get a data set before I'll give you the test paper itself. So about week 11 or so, I'll give you the data set or sets I want you to look at. I think it may be just one data set. I'm not sure. We'll see how it goes. But you will get to play with it. You can do what you like with it. You can write all your code, all those kinds of things beforehand. But the due date I'll give to you, and the exam paper will be given to you about a week in advance. So I'll tell you what I want done with the data later on. But by the time you've got to the end of the course, you'll have an idea of what to do with data in the first place anyway, right? So you'll have some fooling around the data. You can write stuff beforehand. But as I say, the due date, you'll probably get a week or so to do the exam, submit it to me online, and it gets marked online, excuse me, and all done before you actually finish your other exams. Any questions so far? Yes? No, the lab test is outside of the lab class. You can do it in the lab class if you wish. As I say, you can use any resource but not the person. So the idea is you do the lab in the lab class, and you go home afterwards, do the lab test afterwards, and submit it online. The links will appear on LMS later on. Yes? One will be available. They'll be at least a week or so beforehand. So the first lab test is due next week, Friday. I expect it will be the LMS this week sometime. So yes, it'll be there this week sometime on LMS. More questions somewhere? Yep. The exam is untimed. It's a take-home exam. You can take 2 hours if you wish. Time yourself. Any more questions? Anybody feeling a bit unhappy?
Not unhappy. Like, I've done probability and stats, but that was like 10, 12 years ago.
You're only about 10 years old.
No, 12 years ago. So
when you're 2, you do stats? Anybody scared? You're scared. Are you scared?
Week first.
You're scared. What are you scared of? Lines, kindness.
I did STAT2402.
When was that?
That was last year.
Yeah.
And the material that I see now before doesn't appear to be covering things like, certain distributions and t-statistics.
Wasn't covered, right?
Hope so.
Wasn't covered before?
Wasn't covered.
It will be covered, That's why in the lecture notes you'll find that stuff. And we'll go through some of that now, in fact, as well. But yes, you'll pick up those things as you go through. So if you look at the lecture notes that are put online and the recorded lectures, you'll find some ideas. And we'll cover some of that now as well. Any more questions? Did I?
I mean, yeah, and just resources to look at.
Yes.
Would you recommend someone, like similar to which is how I did the stats over a decade ago? And I don't remember, would you recommend going through everything? Or is it
No. You'll pick up stuff as you go through here, right?
Right.
Yeah. I mean, the t-tests are the basic stuff we do in statistics. Everything just boils down to a t-test in the end, somewhere along the line. Or a z-test, close enough, right? So you will find in the lecture notes I've given you, the t-test code is there, some expression as well. So as I said, we'll discuss some of that now as well, but we'll pick up things as we go through here, right? The idea is, in the lectures here, I don't lecture. It's boring. Standing there talking to students, and I say that again, talking to students is boring, right? The conversation is much more interesting for both of us, I think. So we'll be talking most of the time and looking at problems and issues. Of course, I'll cover stuff as well here as well. But the idea is basically, let's work out our problems and sort them out together. Yeah, you get to the lab, you've got two demonstrators there, fantastic guys as well. They've done the course. They're both qualified statisticians with honors degrees. One's doing a PhD, in fact, so you'll find they'll be helpful as well. I won't be in the lab myself all the time. I'll drop in occasionally, right? Because I'm a busy person, very, very busy person. But nonetheless, yes, I will be there as well. Any more questions or any more fears? No, I've got too many of those. You can make yourself one. In fact, on the line on LMS, I'll put together a discussion board. So you can bounce questions of each other. Sometimes tutors will jump in and answer questions as well. I'll jump in there occasionally. But if you want me to look at something in particular, email me, and I'll know what to look at, right? Now, I'm pretty good with email and answering questions in email, and I'm very hard to get riled, but what riles me sometimes is stuff I've sent 10 times and somebody sends me questions. When's the first test due? It's online. You look here, first test. Tells you there, right? So if you can't, before you ask me a question, look at the unit outline. Most of the information you require about assessments, everything else is going to be on there. Yeah? So look at that first. Any more questions? All good. All right, let's carry on. So in the first week, we did go through some R stuff. Now, I'm hopeful that by this stage, all of you must have this on your machines. Is there anybody who doesn't have a machine? First question. Okay. Anybody who doesn't have R or R Studio on your machine? You must have it by now. It's easy to put on there. Yes or no? All got it? Great. If you don't know how to do it, look up YouTube. You'll find videos how to do it. The thing is, it's pretty simple and straightforward. If you can't do it, don't be shy. Ask. Now, you'll have some idea of libraries. We've been using them, right, already in the R code we've seen. The two other things we haven't done yet is R Markdown and ggplot. Ggplot is a fantastic plotting tool in R that just about does anything you want. It has very fine control and gives you very fine control and adjustment of graphs. You can almost sketch anything you like in that. As I say, it's the top library we've got for plotting. So today we'll take a look at some, we've done some of the lecture notes online with linear modeling, all the rest of it. Is there anybody who doesn't know what a regression model is? Regression model? Regression model? No? Okay, so all we've got is the simplest example, simple examples are great. Let's take a look at, say, the measurements of height and weight of people. We're trying to put a regression line or straight line or some kind of relationship between the height and the weight of a person. So we know taller people are usually heavier, right? So you might get data that looks like this. Old stuff. So I get data that looks like this. This is the height of the person, and I'm trying to work out how the height and the weight are related. So generally speaking, as height increases, so does weight. You get some odd people, you know, tall people who are really built like a broomstick, no weight at all, right? Just bones. And you get some short people pretty well built. But overall, you've got some relationship there. So what we do is we look at this idea of a line of best fit. So what will the equation of that line be? In other words, how can I get the equation between y equals something, maybe some constant times some other constant times height? So all there is, straight line equation. So we do that, the equations, you can find the formula for these things. I'm not going to bother here, but as far as R is concerned, you can put the data in R, you can put the linear model equations in there, it gives you the output. That's what it does, right? The relationship there. The things we're interested in is going to be this. Is this a good relationship? In other words, we want to assess the quality of the relationship, assess the relationship. Is it a good model? Is it an adequate model? So the good model has, the issues with the model is that every model has assumptions. And so does this. So this kind of idea here is what we call a linear model. By linear, I mean essentially linearity here is in the parameters or the coefficients a and b. If I take height as a square, it is still linear because the a's and b's are linear in that sense. And linear essentially means adding things together in some way. So this is a linear model. You get some idea as you go through with this. And so things like ANOVA, if you've seen that before, and two sample t-test, even one sample t-test, all those things essentially can be thought of as linear models. And so the assumptions here for this kind of regression model is going to be, the first assumption is going to be that a linear model is appropriate. Linear model is the right one, in other words. And the second is that the variance or the spread of the data now by constant I mean essentially there's a model thing here. It means essentially there's no change in it, and I'll get to that in a second. But the usual linear model works like this, and we'll get to some of that. It's in the lecture notes slide as well. What I have is I've got observations here, y, I use funny words like alpha and beta, and there's some error term involved. We put a y there, I there, because essentially I gives me the data is 1, 2, 3, 4, y1, y2, and 3, 4, and so on. So I've got my data here is the point y1, y2, y3 labeled in that sense, just to collect them and have them identified in that way. And you can see that even if I do fit a good straight line here, this isn't the best straight line, okay, but never mind. What you'll find is that if I even change it, you won't get all the points of the line. So in other words, yi isn't exactly on the straight line with xi as the equation. And I'm going to get some error or some residual or some what we call random variation term. So in other words, I'm trying to explain how height varies with weight. And in other words, I'm trying to explain the variations in weight by height. And I can't explain all the variations in weight by just height. Yeah, as I said, you get people of the same height with different weights. Yeah, other things involved as well in there. What other things can affect the weight of a person? One thing, straight away. Raise to you.
As in a physical thing, or?
Yeah, physical, biological. Demographics such as, this wide, broad. Sex.
Built.
I was going to say the diet.
Yeah. First thing is sex. Men, women, different, same heights, different weights. Genes, yes. Race can make a difference as well. What else? Heights, there we've got that as well. Age. Anything else? Diet, yeah. I'm looking at physical measurements mainly. Cholesterol, yeah, okay. What other things? Belt size, girth, yeah? Same height, one's built like that and one's built like this, yeah? Girth, lots of things other than just height, right? So if I'm trying to explain weight just by height, I haven't got much of a chance. I'll get a model of some kind. Won't be the best model. So I need to expand the model, but for the moment, I'm assuming here that the linear model is appropriate and that the variance is constant. But that I mean that if I take a look at what happens here with this error term, so the model says this. It says that the average value of the weight, and we write this as expected value, average value of the weight is a straight line equation. That's the average value. And now with the error term over here, and the error terms have a normal distribution with mean 0 and variance sigma squared. So if these kind of symbols don't make sense here, this essentially means average or expected value. That means if I take a look at people of different, people of the same height, and I look at their weights, what I'll find is there'll be some variation there. But the average is the straight line thing. So if I can expand a bit more and say, look, what I've got here is, this is height again, and this is weight. So my average will be a straight line like this. But at each of these locations here, what I'm going to see is a normal distribution for the weight. So people of the same height can have different weights. For those weights for that particular height are normally distributed. And if I look across at different heights as I go through there, the mean will change by the straight line, but the variance remains unchanged, right? So these are all normal distributions. This is a normal distribution, some mean, which is alpha plus beta times height, but the variance is remaining constant here. That's what I mean by constant variance. Now the other aspect of this is this. If I actually take a look at the error term, as I say, if I take the mean away from this, if I subtract the means, all these, the mean values from there, this line becomes flat, essentially, because the slope or the interest has been taken off. So the error terms are normally distributed, and this is how I can test to see if my assumptions are satisfied. I look at the error terms and see if they have, the mean 0 will be okay, but the variance that I'm looking at, constant variance over here, so if you look at the notes we had earlier, what often the common thing we do is going to be we plot the residuals. By residuals I mean what I have got is I fitted the line now. Go back a little. Here is my line, this bit, this here is my line, the value I get from the equation, and this here is the difference. The residual here is always going to be observed value minus the value I get from the model, observed minus fitted. So the fitted value here is on the line. The observed value is somewhere here. You can see the observed value here is lower than the line, it will be negative. In some other cases, the observed value is above the line, it will be positive. Overall, if I add the residuals, I get 0. All of the variations are going to be 0. But if I take a look at plotting the residuals, what I'm expecting to see is a constant variation. So that means it should really look like this. If I take a look at here, the fitted values, and here if I put the residuals, residual essentially meaning yes, what's left over, then I'm expecting a band around 0. Constant variance, right? If it's not constant, what will it look like? Well, often it looks like this. Fanning outward. So as the fitted values increase, you can see as the fitted values increase, my variance increases. Or it could be the other way around, fanning inwards. So here, as the fitted values increase, my variance of center of the spread decreases. So the most common, the most serious issue with the models are going to be the constant variance one. We were listing assumptions before. If I can go back for a little second here, we said linear model is appropriate, variance is constant. And of course, the third assumption here is going to be that the error terms are normal. And each of those has to be checked, and each of those is checked by looking at the residuals only. Nothing else is required there. Residuals tell you the whole story. Once you put the model in there, fitted the models, what's left, the residuals, is the observed minus fitted. Take the fitted values away from there. What's left is the residuals. The residuals contain all the information on how good the model is, as well as what issues there are with the model. Yep. Only one predictor, 100 predictors. Oh, it's applicable to all of those models, all linear models in that sense. Yeah? Whether you've got 1 or 10 predictors, it makes no difference how many explanatory variables you've got. The model assumption is the same. The linear model is appropriate, variance is constant, and the error terms are normal. They remain. Those three assumptions are there for all linear models we'll be looking at. Any more questions? Yeah.
When we don't have a good model, that's just indicating that we're using the wrong variables?
Not necessarily. We'll get to that in a second. So assumptions have to be checked. So we'll find whenever I have fitted models, one of the basic things we do all the time is I'll plot the scatter plot of the residuals versus fitted values. That tells me about the spread, if there is any change in spread. And it tells me if the model is a good one as well, and I'll get to that in a second. The other thing I'll do on almost always is plot a residual, histogram of residuals to see whether it looks like normal or not. And also the QQ plot, normal probability plot, so see whether the plots is at least close to straight. So those are the assessments of normality. The assessments of constant variance and model being appropriate is from the residual plot with fitted values. Yeah? And if you've got more than one variable, you can look at it with variables as well. Yes? in that case, my fitted values will be what my equation tells me as what my equation predicts as the actual weight for a height. Yeah, what the equation tells me is my fitted values, and once I subtract it from the actual weight I observe, what's left is the residuals. Yes. Any more questions? Yeah.
Going back to the multiple model, multiple variable model, the lab assignment has such a situation.
Yes.
And when I plotted the residuals, I got a sort of U-shape.
Yeah. All right. So you've got the basic ideas of this. I'll get your question in a second. Basic ideas, right? And how you fit the models, of course, you've seen the R codes on the lecture notes beforehand and the slides today as well. The R codes available to you. Copy, paste, change the variables. Yeah. The first idea of learning something new is mimicking, isn't it? Copying. Yeah, until you get familiar with it and you start doing things yourself. Good? Any more questions? Right. So here's an example I'll go through today, now, in fact. So if you look at this, this is my lecture notes for this week. It's an R. Yeah? And I link R with LaTeX and I get my PDF file. If I don't like what I see in the PDF file, I go back and change the R code. Straight away, directly, right? It makes it so easy to produce documents without having to fiddle back and forth between, say, Excel and Word or whatever else. It's really, really fantastic. Now, while we're with this kind of stuff over here, let me just do a couple of things, see whether this works quickly without having to fuss too much. I don't have the directory here unfortunately, but I can change it to, so in fact, directory setting is going session and change working directory to the source file location. That should work. I should, I hope, be able to read my data now. No, I don't have that particular data file here. Where is this from? Oh, okay. Give me a second, I'm going to get my data in there, we'll be fine. Excuse me, sometimes plays up a little bit. So the fish that we'll play with today in the labs this week at least. I had this already put it there. What's this? Okay. Give me a second. I thought I had put the data there, but I haven't got it there yet. Should be in here. Okay, have a look at this. So what I want to do is illustrate what you're just asking me a while ago about questions about how to build models. So what's going on here? Where did I save this? USB disk. All right, so let's have a look at this data. I've got variables x and y there. The first thing we do usually is, if you read data into R, one of the first things you should do is look at a summary for more than one reason. If you haven't read the data in correctly, you will not know unless you look at a summary. You try fitting models, nothing works. Summaries here, I've got some data. Minimum x is 1 and maximum 40, and y values there. The other thing I want to know is how many observations I've got there. So the number of observations comes from taking a look at the number of rows in this. So simply I can take a look at n row of what have I got here? Mult 40 observations. How many is important as well. So I'll leave this file online so you can look at this. Plot of the data. Now, how many of you think is straight line? Not very straight line, is it? We have a curvature chain there. Exactly what model should I try? Do I try y equals x squared, y cubed, 2 to the x, 3 to the x, e to the x? What do I try? Where do I start? You start simple. So I put in a straight line. Yeah? That's what it looks like. So my first, and I'll leave this note as I say online for you to look at it. The first thing is I put in a straight line there. So this is my command is lm y versus x. So I'm putting a straight line, oops, of y against x. Straight line model. Look at the summary of that. Now look at the summary here. Can you all read that? I reckon I can make the code, the font a bit bigger. Where is it? Something to do with maybe view, I think. Ha. What's the difference between multiple r squared and adjusted r squared? Well, multiple r squared is just the usual correlation coefficient, right? Squared. Adjusted r squared adjusts it for the number of variables you're fitting. Right? Adjusted was what you look at. The other things you'll find is that you'll find models give you often is this idea of AIC and BIC. And those things we'll see later on are also measures of the goodness of fit. But here the multiple R squared, just R squared, 0.96 or so. Now, most people who do statistics don't do it properly. They don't look at the data, they don't plot the data, they go bang with the model. And they get a model like this of saying, look, multiple R 0.96, fantastic model. And some of them are lucky enough to come and ask us in that case, and we say, rubbish model. They say, why? It's got an R squared of 0.96. If you look at data in many areas like psychology, for example, even student data that I work with quite a bit, has so much variation in there that often you don't get an R squared of anything about 0.6 or so. That's all you live with, right? Because there is so much variation in there. People just aren't uniform. They behave different ways. So you can't get an R squared very large. Here is 0.96, and people will say, fantastic model, they'll stop there. But you see, we aren't normal people, are we? We're statisticians. Here's a plot of the residuals. Your idea, U-shaped. So all the information on the model after I fit it is in the residuals. And so I look at the residuals of the fitted values against the residuals. What does this look like? Parabola, quadratic, squared, right? So it's telling me, hey, put an x squared term in there, right? So I put an x squared term here. Now, should I keep the linear term, the x term here, or take it out and just put x squared term? Well, the idea, the way stats works is, if I have the higher order terms, I must also keep the lower order terms, unless there is reason to delete them. So here, what I'm doing, if you can see in the code, is all I'm doing is updating my model here. Take this first model I had, and I'm going to add the x squared. So the I here essentially is a function calculator. It says don't do the calculation, but do the calculation in the model itself, right? So it puts the x squared term in the model. If you just put x squared in there, it doesn't work. You can try it here. So here I'm actually going to update the model, put my x squared term in there. And here's a summary of that. You can see my terms here, both the x squared term and the x term are both significant, which is great. And my R squared has increased to 1. Of course, now that's 1 within a calculation error or the underflow of the machine, yeah?
So if we want a proper fitted constant for a straight line, is that correct? And so we try to change this to something like a constant, is that?
No, we're adding a squared term in there.
And what's the square term?
Squared is parabola. Parabolic things look like x squared, right? So I take the graph of y equals x squared. It look like this. So there's 0, 1 will be at 1, 2 will be at 4, 3 will be at 9. Yeah, it'll be a square. That's what it looks like, parabola. Yeah? Good. So yes, so what I've got is I've added the x squared term in there. Now it looks fantastic. My R is 1, at least within the error of the machine store, right? 0.9999, something like that. So, good days, happy days, fantastic model, right? Stop there, do we? What do we do next? Assumptions. What's the first thing we should do then? Plot the residuals. Look at that. It's not bad, you know, it's within 0.1, 0.4, so it's much tinier as well. But there's still a pattern of some kind. Now, you might find that little square thing looking like that again to start off with, but the major pattern I see is this one, the one that goes like this, you know, the up there and then this way. And so that looks more like to me a square root term. So square root function looks like this. Yeah? And so what I'm going to do next is put a square root term in there. So there is my square root term. And summary, fantastic. All three terms, my x squared term, my square root term are all significant with very small p-values. So again, is there somebody who has not seen p-values before? A p-value will tell you essentially if this term you're looking at is significant. So basically the idea is, once I fit a model of that kind here, I've got something like y equals, let's go simple, alpha plus beta x, and my error term. I want to see whether this beta actually is 0 or not 0. Remember, just 0, which means I've got y equals alpha, constant. There's no relationship between x and the y. So my H note here is going to be saying that my beta is 0. This is my null hypothesis. I'm supposing to start off with that y and x have no relationship at all. The null meaning nothing's happening, right? Essentially, that's the idea. And H1 says, no, there is something happening. My beta is actually not equal to 0. In other words, this is when we have a significant relationship, meaning that x and y have something significant between them. And that's judged by the p-value. The p-value essentially is a probability of something. It's hard to explain without becoming technical. Essentially, it's saying how likely is it that you get data that looks like this when beta actually is equal to 0. If beta is 0, what's the likelihood essentially of getting data that behaves of the kind I've got here? And so if the p-value is small, that means that this is not true in very broad terms, meaning there's evidence against my hypothesis of beta being 0, and I then will tend to believe that beta isn't equal to 0. So p-value is what we use to judge hypotheses or judge these models. So in this case, all the p-values are small. The usual story is we take the p-value of 0.05 to be a benchmark. So usually what I take is what's called alpha or significance level. Is taken as 0.05, because when I see p-value small, small means nothing at all. I need some idea what small is. Significance level is 0.05, meaning a p-value less than 0.05 is significant. That means I've got a strong relationship there or some relationship there too of some kind. Let me close some other files so I can see everything in one. So in this case, all my p-values are small. Fantastic. Good model here to start off with. But of course, I don't judge models by looking at how small or big it is, the p-value wise. What to judge them by is we take a look at the plot of residuals. And there it is. Now, in fact, residuals are very small indeed. Look at the scale on the x-axis, on the y-axis, it's 4 times 10 to the negative 8, almost 0 essentially, right? Very small indeed. And there's not much pattern. You might think, well, there's some change in scale here because you see it's quite small here and tends to sort of go upwards here. Yes, maybe, but the thing is so tiny anyway compared to the value of the actual variables. The variables are 1, 2, 3 till 40 for x, and up till about something like a few hundred for y. So this is tiny compared to that. So I'm going to stop there and say this is a good model. So if you look at this, I want to open something else up. All that's in this PDF file, which I'm going to put online, and the R code as well. And it's all explained in there. So if you look at this, what you find is my model equation, it looks like this. And I can see a typo, it should be a squared, is 10 plus 2.5x plus 0.25x squared, oops, plus 1.2 root x. So you see I have a very complex model there. It starts off looking like a curve. When I put in straight line to start off with simple model, you got no idea what to put in there, put a straight line in there. From there, my residual suggested putting an x squared term, which I did, and then I got a square root term here. So you can build by looking at residuals. Many people don't understand this or know this. All right, your stats don't understand how this actually works. You are now smart. Sorry, you're now smarter. So always these ideas of residuals to see what it suggests as to what you should do with the model. You shouldn't decide what model to fit. The data decides that. unless you've got some other reasons for deciding on particular models. The data decides that. And now, in fact, this is exactly the equation I used to generate the data in the first place. Yeah? So you can see how powerful this is. Simple techniques, very powerful indeed. So use this in your model fitting. Now, this was in one way a simple one because I only had 2 variables. When you get a fish example, I've got something like 5 or 6 variables. The more variables you have, the more complicated things become. So if I've got more variables than just x and y over here, what I will do is, and by the way, here's the fitted value. This is the plot of the data against fitted values. So what I've got here is the data points in the red, and my fitted line on top of that is an exact fit as you would have expected here. So if you've got more variables, it gets more complicated. In that case, you won't be plotting just residuals against fitted values. You'll probably plot residuals against each of the other variables as well to see what it suggests you should do with it. The fish one is one such thing. Now, when you do the modeling, in the fish case, of course, you'll be in the lab together. Of course, you can talk to each other. You should talk to each other, work together, collaborate, discuss, have ideas, throw around ideas. You might end up with different models. In this case, if you do this analysis the way I've done the thing here, you'll get only one model because the data was actually generated from that one single model, and this is a simple model. In the fish case, you might get 5 different models. Your models might be different. The thing to judge the models by, at least some ideas or some guidelines, are these things called the AIC, which is Archaic Information Criteria. This is essentially some kind of assessment of the model, which we'll see later on. And I think I've got them listed here somewhere. Yeah, AIC for each of the 3 models. You can see it starts at about 390 or so and then goes smaller and smaller. The smaller the better. The smaller the better. More negative. The other thing you'll see sometimes is called the BIC, the Bayesian Information Criteria. And it's similar to AIC, but this is a little bit better because it adjusts for the number of variables they fit. If I include more variables in the model, my model won't become worse. If I've got something like, say, the height and weight data, I'm trying to explain weight by height. I've got the weight of the person and the height of the person. If I put in something stupid like hair color, my model won't get any worse. Adding variables won't make the model worse. Taking them away will, right? So if I've got too many variables in the model and that looks to be a better model, I judge that as saying, in other words, I balance that against the number of variables I've got in the model. So if I've got a model that's got a fewer variables and a good fit against one that's got many variables and a good fit, I'll take the simpler one. The simpler models are better for more than one reason. One is simple models are easy to explain. Yeah? How do things actually work? If I've got 50,000 variables in the model, it's hard to work on exactly what does what. Smaller models are easier to explain and understand. And more than that, often we're not just content with explaining and understanding, we're actually interested in controlling. Yeah, controlling. So I'm trying to work out how my wheat harvest goes or whatever else. I want to understand how watering and nitrogen, whatever else I put in there, makes it grow or produce what the harvest is, right? Understand that, that's fine, but I don't control the thing now. Yeah? Question?
When you talk about reflection, there are 2 options, right?
P-values will tell you the significance of the variables in the model, right? But AIC and BIC will compare between models, yeah, between models. So here I've got for the first model I fitted, the first one. The second model you can see is better because I've got reduced AIC, and the third one's even better than that. Question? I didn't. Yes. Well, I just fitted the models over here, right? I just, as I was saying earlier, I decided what variables to enter into the model by looking at plots of residuals. So my first was a straight line model. I've got this plot of residuals looks like this. Suggests to me a square model. So I put a square term in there. My next residual suggests to me a square root term. Put that in there, and I'm finished. The last residual plot has no particular pattern I can pick up. Yeah, now, when you start looking for patterns in the residuals, don't look too hard, because you'll find something. It should be, if it doesn't appear to you directly, like this one here, for example, being very, very clear, doesn't appear to you straight away like that, it's not there, right? Now, there are some cases, of course, you have to look more carefully for reasons, but you'll learn those reasons with experience, right? Here, for example, people will say, what's going on here? But to me, it's a square term that's the dominant term, right? The other one is squares. I worry with the square term. The square root term is the more dominant term. And in here, if you look hard enough, you'll find, well, there's some smaller values that I was saying here. Maybe there's some fanning out here. But no, because these values are so tiny compared to the actual value of the variables themselves, this is just ridiculous. This is nothing there at all. So be careful how you look at this thing. If you look hard enough, you'll find something. All right, so let's proceed. We'll stop for questions in a while. Some problems here with files that I'm putting in there. I'll fix this code here. But I want to look at this in particular here. Now, when I put this online, you'll be able to read this as well. Apparently, my data wasn't in there when I put this thing in there. This is power data. This is what the next data set is looking at our thing is the cost of power over time or something. I can't remember the details of it. But there you have a choice of models. You can either fit a quadratic model, a square term in the model, or you can put a log term in the model. And the square term fits better than the log term. But the problem is you're looking at the cost of electricity with, I think, usage is more appropriate, not time. What you expect to find is the square term actually, data looks something like this essentially, overall. The square term tends to do this kind of stuff. Fits very well and then comes downwards, you see. So my data only goes up till here. My data finishes over there. So the model for the range of data works very well. But beyond that, it tends to go downwards. So that it means to me that as I increase my power consumption, my cost should come down, which is not sensible. So instead of picking the model that seems the better one in the context, I pick a model that's a log model. Now, log function looks like this. It goes up in the same way, but then flattens off. It doesn't come down. It tends to keep going up, but flattens off as we go through, right? So it goes up much more slowly. That's more reasonable, because as my power consumption increases, my cost won't go down. It may flatten off. So in the context, I pick the model that may be the worst model, but makes more sense. Yeah? So that's the illustration there. I'll leave that online for you to look at afterwards for yourselves. So I hope I'll explain something about how modeling works in this context. When you get to the lab and start with a fish example, I've given you some guidance there, but the lab assistants will also guide you. But by all means, don't be scared of making a mistake. I know the person who never makes a mistake is the one who never does anything. Yeah? Life is full of mistakes, isn't it? How do you learn otherwise? Well, there's three ways people learn, actually, essentially. You learn by listening. So somebody tells you, don't go there. And you don't go there. Done. Finished. And otherwise, you say, I don't believe that. I will do something else. So you look at somebody has gone there and look at his life and say, my goodness, I shouldn't go there. Or you can say, I'll go there. You go there and you get kicked and you say, shouldn't come there. Yeah. So likewise, you can learn in various ways. So I hope you've learned by listening here as well as by experience, by trying things. Go in the lab, make mistakes. Sometimes things don't work. Doesn't matter. As I was saying earlier, your model is different from someone else's model. But you can judge the thing by AIC, BIC. If my AIC is lower than yours, a better model. Unless, like I was saying with the power example, the context is more important. But you see, the thing is, with complex data sets, you've got so many options of what you do there, that sometimes you get two models that are equally good. You can't choose between them, right? So you'll choose on the basis of context again. What makes more sense? What is simpler usually? The simplest models are the better ones usually, right? Always go for simplicity, simple models. So try that in the lab. Any more questions before we carry on? Not at all.
Multiple variable situation. You've only got one there in that example. So how do I know which term to square?
Ha. I was saying earlier, if you've got more than one variable in the model, you look at plots of residuals versus each of the variables. And then I'll tell you what to square. Yeah, the one that looks like a square is the one you square. Maybe it looks like a log, you'll log that. Sometimes you've got problems where various, maybe more than one variable has the same kind of pattern. Well, in that case, instead of looking at all the variables and changing them all, you will actually transform your response variable. Yeah. So I've got something that looks like this, for example. I've got, say, variables x1, x2, x3. I've got, say, x1 with my y, and I've got x2 with my y. It also looks sort of similar like to that, like to whatever else. So this looks like essentially exponential. You might say square, but exponential is the more favorite one we'll look at usually. Instead of trying to say that y is equal to, say, something with, say, exponential of x1, and something times e to the x2. So exponential function is the e to the whatever function. I'll do that in the reverse. I'll say no, I'll log it instead. I'll take a look at log of y, and that becomes a plus b x1 plus c x2. Now these a's and b's are different to the previous ones. Well, that makes me a straight line graph with a log of y instead, right? Now, you might even try that with a fish example. See how that works. If you think that several of the plots look like this with the data, you might look at, say, well, I'll just log it. But the first thing to do is try the simple linear model and see what happens there. Yeah, simple is good. Simple is good. Any more questions before we move on?
You looked at some of the shapes like the parabola and said that looks like an x squared and that one looks like a square root. Is there a reference?
Yes, there is. So here is a reference. Yes, here's the reference. This is a straight line, right? Y equals a plus bx. This is y equals x squared. This is y equals square root of x. That looks like the square, but it's not. It's y equals e to the x, which is a bit more steeper in the end. And this looks like a square root, but it's not. It's y equals log x. Now, sometimes you might not find much difference between the square root and the log in your model, right? But as I was saying earlier, you might have reason to pick one and not the other one because interpretation is easy for one than the other. Interpretation is key. How you interpret the model actually means is very, very important. You can find all these. If you look at, say, graphs of functions on Google, you'll find them all there. Yeah. Now, unfortunately, statistics requires a lot of mathematics. It requires a lot of mathematics, which most of you don't have. Yeah, it requires quite a bit of mathematics. So, but you can still do a lot of statistics by understanding how the maths works without actually understanding or doing the maths yourself. Yeah, it can work very well. But you'll find occasionally you get stuck with some things that you require advice on. Even if you think you're a competent statistician, you'll find problems you just can't solve because you know, when you're using what we call standard models, that's fine, but when you have to make it unstandard, non-standard, make your own model, create your own model, you can understand how things work. And I talked to students quite a bit about this. Essentially, what we're teaching you here in this course, by and large, are still basically recipes. Because without the mathematics, you won't get the deep understanding. Yeah, but you'll still do quite well with that. The unfortunate thing is when recipes go wrong, and I'll show some examples of that. So you won't just go through here standing and looking at this kind of stuff all the time. I'll show you some videos as well, some fun stuff as well. Now, lectures are meant to be interesting and fun stuff, not just technical stuff all the time and make it boring. So we'll look at some videos as well as we go through, some really interesting videos, I hope. All good with this so far? Shall we carry on? Don't worry about that. It's complex numbers. It says complex numbers above that, right? Complex numbers.
But then it's not isolated.
Don't worry about that. See me afterwards. You know, if you've not done complex numbers, it won't make sense. I was saying earlier, I was saying in the lecture notes, complex numbers if you've done them before. Don't worry if you haven't, right? Don't worry. Any more questions? I think we carry on with this, and then we can pick up questions in the lab afterwards. So let's move on to the lecture slides for this week. So outline we have looked at, no problems. We have looked at this lecture. These ones I'll put online later on when I fixed all the problems I've got with the data. Here is what we have this week. So as I was saying earlier, this is lecture notes put together by my colleagues from before, which I'm revising now, so their names will disappear in time when I make this my own. So first thing is, we've done one sample, two sample tests were in last week's lecture notes. Now you might understand everything from there, but by all means keep asking questions in the labs and other places, you'll understand some of that. But once you've seen those things, you can now Google them yourself and understand what context they're used in, right? And understand some of that. Binomial model tests also I've covered there, but we'll cover them again later in this course. And we've just revised what we call the normal linear regression models, where the assumption is that the residual terms are normally distributed. Yeah. Now, you'll find most people will say, I've got something like a model with y as my response variable, and they want this to be normal. But that's not the case. It might not be normal, but the residuals will be normal. That's what you're looking for, right? Because in many model situations, you won't find this. For example, if I take a look at the height and weight example again, I take a look at a plot of height and weight histogram, for example. So this is the plot of the weight. Most likely, you'll get a histogram that looks like this in shape, at least. You know, something that looks like this. See, normal would be this, right? Normal would be something close to this. But what you might get is something that looks more like this. What I'm seeing there is not just one normal distribution, but two of them. So I've got something that looks like this, essentially. I've got something that looks like one normal, another normal put together that way. And these two groups I'm seeing in the data may be the males and females. Yeah? In that case, I won't expect this to be normally distributed. Once I've taken the means out of there, if I take, this is my average over here, I subtract that, then that curve shifts over here. Subtract the mean from that, that also comes over here. Residuals in that case will be normal. And that's what you're expecting to see. The residuals should be normal, not the actual response variable itself. Yeah? So in multiple regression, the response doesn't have to be normal. Residuals, you need to be normal or close to normal. If you only got x and y, two variables, yes, your response in that case will be normal. So this is what we've just done over here, as we were saying earlier, Gaussian or normal regression we've just covered here today. We'll cover that also in lecture in labs afterwards. So we'll work through those as we go through and hope understand them. We'll do them. Your first test, which will be in week 3, is based on this stuff, normal regression stuff, because that's what you'd have covered in the lectures, in the labs as well by this stage, yeah? So, as I was saying earlier, this should be more titled more appropriately as analysis of discrete data. So, the problem is, the data we've seen so far is continuous, which is red here. Is this red here? Yep. Continuous data, right? What we're looking for is not continuous data. So if I change my data from, instead of saying weight versus height, where weight is continuous, if I look at something else, for example, I'm looking at the number of, I'm looking at a population of some kind. I'm looking at a population of voters, be simple. And I'm working out how many of the voters will vote Labour in the next election. Now, my data is not normal anymore because it's counting data, discrete data, right? That changes everything. In other situations, I'm looking at, for example, the number of failures I get. One of the pieces of work we did was looking at the BHP Billiton conveyor belt wear out. Yeah? Working out how many belts wear out. Not this number of belts, is number of belts, counts. Yeah, looking at things like diarrhea of children. We did some work with that on Tanzania, looking at children getting diarrhea. We're counting how many children actually have diarrhea. These are count data, discrete data. They aren't normal anymore. If you try and fit a normal regression model to this, your answers will be wrong. Not just maybe about half right or so. They could be completely wrong and give you completely the wrong picture of what actually is happening there. So the count data can't be modeled in the same way as we have done so far. Some things have to change with it. So this is binary data or count data. Either things like where you've got two outputs, two outcomes, 0 or 1, heads or tails, for example, tossing a coin. That's binomial. Or you're looking at count. How many people who had accidents on the road wore seat belts? And looking at whether there were seat belts or not, and we can look at how many of them had injuries, serious injuries, maybe not so serious, or maybe dead. This is in your lab for this week. You would have seen this by now. So that kind of data we're looking at here is not normal distribution anymore, it's something else. So I need to look at something else. These kinds of models are called generalized linear models. What we saw was linear models. Now we're going to generalize them. So it applies to this kind of data instead. Yeah? So we'll look at some simple techniques as well, but then we'll look at some more advanced techniques. Simple techniques will be okay to work in many places, but the advanced techniques allow you a lot more facility. So as we saw earlier, you must understand some knowledge of the fundamentals, concepts, and statistics. Me. Apply the modeling to real data. Absolutely require packages like R here. And the most important part of doing all that is to be able to communicate the results of these analyses effectively to non-statisticians. So don't say the p-value is this. Don't say the coefficient of this is that much there. Tell me what it means. If I'm looking at diarrhea, now to know what the children ate before and the last 2 weeks and whether they've got diarrhea or not, or what their body weight is, or what their birth weight was and diarrhea or not, I need to explain that, for example, children with low birth weights are more likely to get diarrhea, that kind of stuff. People who don't wear seat belts are more likely to die, that kind of stuff, back in the context of the question itself. So it must be non-technical from the stats point of view, but technical from the context point of view. And the words, as I say, you'll pick up and learn up as you go through. Assume knowledge, well, we did say this, but all of this has been covered in the R lectures last week, and we'll keep working through these things as we go through here. Now, in the last part of the course, we take a look at some things called likelihood. Likelihood essentially is a probability-based idea. We're trying to maximize things, maximize functions, and that's mathematical. That requires this thing called differentiation. Now, in the past, we've actually glossed over this, I think, very badly. And many students here in the class, I would expect, have not done any calculus. Check some smart ones from before, yeah? But don't worry. I intend to, in the last part of the course, cover this calculus part as well. So in other words, I'm not just teaching you recipes and saying, do this, will work, don't worry about how it works. I hope I'll get time to teach you how this actually works. But there's more fun stuff to this. This actually will get tested towards the end of the semester, maybe in your last test or so, right? You've got time to learn that as we go through here. And I don't think it will be in the final exam in any form or shape, so don't worry about that. So we'll pick up these things as more knowledge that you should have and makes it easier for you, and see how this goes. So R, as we say, we'll cover week by week as we need it. It requires some idea of probability and statistics. We'll cover some as we go through here, as far as probability goes here. We've done this part already. Exponential logarithm functions, you have some ideas, or you will get some ideas as we go through. Essentially, we just said exponential is number e to the x is the exponential function, and that looks like this. Essentially grows very fast. Here it's 1 at 0. The log function is the inverse, goes the other way around. It flattens off quite fast, but it keeps growing. It doesn't actually become straight. It keeps growing, but it flattens off very fast. That's log of x. Now, you'll probably find people write this as ln x as well, and that's fine. I'll use log or ln as either way, but in both cases, I'll just mean log to this base e here. So this essentially means log to the base e of x. If you've done none of logs or exponentials before, let me know, email me, I'll put some notes online for you to look at. Read through those, ask questions afterwards. All that stuff you can look at yourself, no problems. We said this is the textbook or course textbook, but it's not necessary that you have to have a copy. You can look at some of that online or on the library. There's a very high demand section of the library that contains that book, several copies I think, but by all means, if you can find the book, look at it. In the latter part of the course, we'll look at this. First part, we'll look at all this stuff here in those chapters, and the latter part, we'll look at some other chapters of the book, but other places as well. But as I was saying earlier, lecture notes will be enough. Everything you need will be in the lecture notes. Test, be careful how it works. I've got there, I think, in 3, 6. This is not going to be a 7, surely. I think it's 3, 5, and 6. 7, 9, 10, right. 6 tests, open book, take home. You can do what you like with it, but don't ask anybody else. I'm sure you can all be trusted. Yes? Trust yourselves. Do it yourself. Make mistakes, learn from there. Last semester I taught a very difficult third-year course. And the pass rate was 100%. The only thing I ask students to do is stay with me, work with me. Do you know when students decide to fail a course? Because of course, failure is a choice, right? Students decide to fail a course in week 1 of semester. Why? It's too hard. I don't like the lecturer. Yeah? Those 2 first things. Too hard, don't like the lecturer, don't like the subject. Those 3 things make students fail from the day they come to class, if they come to class. Because it's hard to recover from there, right? Because by the time they realize I must do something, it's week 5 or week 6, and the thing is, I'll try again next semester. How does it work with me? If something is harder, hey, I am really smart. But both things are hard for me as well. Something really hard. If things are harder, you increase your effort. If you don't like the lecturer, don't let him or her affect your life. I've had bad lecturers in this place before. I've been a student here for many years. Terrible lecturers. That means you're required to make more effort. This is the one class you can't miss, because however bad the guy or girl is, there is some things he or she will say that will make sense. I've had some terrible lecturers, but my goodness, the lecture notes were great. I learned from that. By being in class, I know what they were doing. Even if they're doing it badly, I could go back and look at the rest of the stuff myself and do it myself. And if you don't like the subject, again, that's why you need to make yourself like it, or at least do it, because if you don't do it, you're not going to pass. And that comes, of course, back to always my question of why you're here in the first place. Why are you here? If you don't like the subject, don't like your course, don't waste your time, go somewhere else. Simple as that. Don't waste your life. Do something else that's enjoyable for you, right? A university degree does not guarantee you wealth, does it? The plumbers are the richest guys in the world at the moment. Try and find a plumber. You won't get him away within the first 3 or 4 weeks, that's for sure. And I'll charge you a whole heap for fixing just a simple tap. They make more money than we do. Hey, but I think my life is more interesting. Yeah? So, why, you decide why you're doing something first before you start doing it. Because if there's no reason for it, you're not going to do it. That's the first thing. And choose stuff you like. Yes, okay, there are sometimes that you have to do things you don't like because the choices you make need this thing. It's part of the deal, isn't it? Life is like that. But again, as I say, if you don't like something or it's hard for you, increase your effort in this. Increase your effort. And this is something that's very close to me, and I really work in this quite a bit with students in many places. I go to some high schools and work with the students. See, the thing is, people come from high school to university, and they do very well in high school. But that's high school, yeah? Year 12. University is suddenly all the way here. Now, you can't expect to do the same in high school and achieve the same grades in university. Things have changed. you also need to change how you do things. Nobody tells you this. Nobody tells you this. You must change the way you work in university. Come in the same as high school. If you want something you have never had before, you must do something you've never done before. Change the way you think. Change the way you do things. Work out things better. Yeah, that's an entirely different story altogether, but this is part of, maybe my interest as well. Change the way you think and do things. You'll find your life will be altogether different. You can do lots of things in many different ways. And I'll give you some demonstrations later on. Maybe you don't want to waste too much time here, but we'll work on that before in other lectures. 40% take-home exam in the end, open book, open everything, except again, as I say, you can't ask another person. So, population proportion. We've revised linear stats models altogether, so I'm not going to spend much time with that. The idea with probability models is that that will actually allow you to model uncertainty. So when I say that there's variation in the data, I need to understand what the variation is, how to describe it, and that's described in these mathematical probability terms here. Now, we don't do a lot of that, luckily, in this course. We'll do some at the end of the course. But the basic idea of the modeling is I want to understand the data generation process. How is the data actually generated? That's my ultimate aim, to understand that. As I was saying earlier, the model requires interpretation back in the context, and if possible, I want to control that as well if I change things in particular ways to get particular outputs. That's the whole idea of this. And if you apply the correct and nuanced application of models, you'll be able to understand many and get lots of insight in many problems of real-world phenomena, understand really how things work. And we'll, as I say, hope to build some of that as we go through here. So the normal model I've covered in some detail. I won't go through that again here. Sure, I meant here to be sigma squared. No, this is 1, sorry. Sigma squared is equal to 1. So I won't cover that very much in details here. We said earlier this E here stands for expectation or mean or average. Sample mean. So if I've got some data that is from some particular distribution, if I assume this is normally distributed, the sample mean is just add them all up and divide by n. So this essentially means y1, when I is equal to 1, I've got y1 there. When I is equal to 2 is y2, and the sigma means add them up. This thing sigma here means sum, and I let I go from 1 to n. So that means I've got y1 plus y2 all the way up till yn, and I'm dividing by n here. This is the usual average. That's what I'm doing over here. Now, when I average data, things change here. So I might have data that starts off from a distribution that looks like this. Y distribution with mean mu. If I have a sample of size n, and I average the data I get from this, and the averages, say I look at something like a sample of size 400, and I pick several samples of size 400, and I take the average of those things, and you can do this in simulations. When I do that, I'll find the averages are a lot closer. So the same mean will be there, but they're much narrower. Yeah, much narrower. And as I say, you can illustrate this by simulations. I won't do this here. Maybe you can do it in the lab sometime, or you can write yourself. But you can look at stuff online as well here. So what you'll find is that what happens is that the mean remains the same, but the variance becomes divided by n, becomes n times small, essentially, much, much narrower. And this is the idea. If I take my samples to be larger and larger and larger, then I'm more likely to be closer and closer to the actual mean of the population, which is a great thing because my sample size is something, in that case, a controlling factor here. So you can read most of this stuff yourself. We have done some of the stuff like one sample t-test, two sample t-test. There's a two proportion z-test as well. We'll look at these things later on as revisions as well. You might have done this in first year, 1400. They used to do this stuff earlier. Maybe that's changed now for the course. But we will take a look at those again. And so these things we will be looking at in this course here. Linear model, I've done this in detail. I won't spend too much time here anymore. But the basic idea, as I was saying earlier here, is that I'm expecting that the average value will be on a straight line, but around there I'll get variation that's normal with some fixed variance. I will look at the mathematics of this. You can do this afterwards if you want to look at this and ask questions. I've done this in detail. I want to move on a little bit here. So when I'm looking at responses that take values only 0 and 1, for example, presence of disease, absence of disease, agree, disagree, then it's either 0 or 1. I'm counting things like the number of car accidents in some particular part of the street here, number of cars that bank up at a light somewhere, number of cases of diarrhea, number of cases of COVID, a number of cases. Those things aren't going to be normal anymore. They're counts. Sometimes the counts are quite small. So, for example, if I'm looking at, say, and this is not, looking at, for example, what people do in agriculture and other places, let's look at a tree and then look at the number of diseased leaves in a forest somewhere. So I can look at a tree and find the number of diseased leaves. It comes to either 0, 1, 2, 3, 4, 5 or something. If you're lucky, maybe unlucky, you might get 10, 20. But you won't get too many of those. Well, tree maybe 3, 4, 5. Let's count data. If I try and fit a normal distribution to that, it just won't work very well. Unfortunately, people do that all the time. But this is what we're looking at when I said counting. We would count data here. Now, this is discrete data. So the kinds of models we need here won't be the same. So we look at this idea of this generalized linear model here. We're going to model something else here. And I'll take a look at those details in the next few classes. What I'll look at here very, very quickly is some discrete random variables. And this is my focus. You may have seen some of this before. If you have, fantastic. Otherwise, here it is. A discrete random variable takes only certain fixed values. I will be non-mathematical as much as I can here. Takes certain fixed values. So you know the values in advance. If I'm taking a look at tossing a coin, the number of heads is going to be 0 or 1. I know it's either 0 or 1, nothing more than that. That's discrete. I can list the values beforehand. If I toss a coin twice, and the number of heads, so I let this idea of random variable. Random variable essentially is something that has a value that I can't predict in advance. So x here is the number of heads I toss. In 2 tosses, I can get 0 heads, 1 head, or 2 heads. And if I look at the sample space for that, I can get tail, 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 head, head, tail, or head, head. Probability of no heads is this, a quarter. Probability of 1 heads is here or here, a half. Probability of 2 heads is a quarter. That's my table there. I can tabulate the values for that. Now, this is a funny little thing here. We call this probability mass function. All it says is it actually gives you the values of probability. So it says probability that x takes a particular value. So the small letter here is an observed value of the variable, and the large letter here represents random variable itself. Now I can use something else. I can use k here if I want, and then this becomes a k as well. Doesn't matter. But this x is my random variable. This is my x that I've defined over here, number of heads tossed. Yeah? Values is 0, 1, or 2. I've listed those values there. Any questions so far? All right. I can find the mean number of heads. Now, how do I do that? Well, if I toss a coin twice, I count the number of heads. Toss it again twice, count the number of heads. Again twice, and I do this experiment 10 times. I can find the average number of heads in those. Yeah? But I can also calculate this theoretically. And the way it works is simply this. I have the value times probability, value times probability, value times probability. So those things that are more likely are weighted a bit heavier. Yeah? That's all that's going on here. If I do that particular calculation in sum, I get the average number of heads. So I get 0 times 0.25, 1 times 0.5, 2 times 0.25. I get 1 as the average number of heads in the 2 tosses of coin. Now, if you think about the thing, if it's a fair coin, probability of heads is a half. Yeah? If I toss the thing 2 times, how many heads would I expect? Half heads, right? That's 1. Makes perfect sense that way. And why is it going off here? Because my power is just unplugged. That's why it's gone flat. Yes, second account, please. Sorry. So what I found there was the average value of that random variable. Number of heads I can essentially get is 1 in that case in 2 tosses. Now we'll see that in more general in a second, once this comes up again. Yeah. Totally died. No problems. At least it restores things. Great. Okay, so that's how you find the average value or the mean of that. So you just multiply the values with probabilities, add them all up, you get 1 as the average number of heads and 2 tosses of a coin. Makes sense as well. Now if I don't want e of x here, but e of something else like e of x squared, all that happens is I square the things before times the probabilities. So it's 1 squared, 0 squared times 0.25, 1 squared times 0.5, and so on. I get 1.5 for e of x squared here. Now, why might you want to do that? And the reason is that you can find the variance also of random variables. And the variance works this way. Is the mean of x squared minus the mean all squared. So the calculations here, I worked out the mean of x squared was 1.5 and the mean of x was 1. Square this one, subtract, I get 0.5 here as the variance of my random variable. And the standard deviation is just square root. So this is how some of the calculations work. So as in other cases, variance mean here is a measure of central location. It tells me where most of the data will lie. And the variance is a measure of spread. Now standard deviation also is a measure of spread. It's a better measure of spread because it's in the same unit. You see, this deals with square things. If I'm looking at something like, for example, count data as the number of cases of diarrhea, the square is a square of diarrhea makes no sense as a variance. But the standard deviation is back in terms of the number of cases of diarrhea. So it's back in the same units as before. That's why it's a more sensible and a better measure of spread. Okay, example here very quickly. I've got this variable here, x, the values are negative 1, 0, 1, 2. I want to find the variance and the mean of this from what I did before. So please find the mean for me. So the way it worked was, remember, is take the values times probabilities, times probabilities, times probabilities, and add them up. Do that, please. And I can also work out the e of x squared in preparation for working out the variance, and that's going to be the same calculation as before, but I'm going to square things first. So e of x squared will be same numbers but squared first. The first one, and the answer is it for e of x. 1? All good? Next one, e of x squared. 2? 2? So the variance was going to be the second thing minus the first one squared. This 2 minus 1 squared comes to 1. And the standard deviation, which we call sigma of x, is square root, which is also 1. Yeah? Now there's a lot of work in this area, probability theory itself, which we won't go into here. This is good enough for the moment. I want to move on pretty fast to this exercise here, which I'll leave for you to try yourself. Yeah, the solution is essentially there available to you. Check that out for yourself and ask questions if you wish. This is actually from a paper. Yeah, it's not just made of data, it's from the paper here, looking at grizzly bears, number of cubs they have. So have a look at that. Everything I'll do here, I'll try and put in some context. I want to get to the Bernoulli distribution. This is a simple distribution. It has only two values, 0 or 1. It's like a single toss of a coin. I toss a coin twice, I count the number of heads. It's either 0 or 1. And the probability of success in this case, probability of a head in this case, is called P, just P. So P mightn't be 0.5, maybe something else, depending on the context here. So it's a simple one. The other thing is Bernoulli here. So this symbol means x has the distribution or is distributed as a Bernoulli, and the parameter is P here. So this has the distribution, and the parameters go in here. This is the parameter P, probability of success. So it's got two outcomes. We just call it success or failure as generic, so we can apply this in any context we like. Because it's got only two values, 0, 1, I can tabulate the values here in probabilities. Probability of success or probability of 1 is P. Probability of 0 is 1 minus P. Probability is to 1, of course. I can find here the mean is simply P. I can find e of x squared, also comes to P. The variance is going to be the first minus the second square, right? So it's going to be, the way it works is here, this was e of x squared minus the mean all squared. So the e of x squared was P, the mean was P, or also it's all squared. It comes to P times 1 minus P here, and the standard deviation is square root. Bernoulli is a simple distribution. It looks at one trial only, success or failure, that's what it does. Binomial is more difficult. What I've got now here is not just one trial, but n trials of the same Bernoulli thing here. It's like tossing a coin 10 times now and counting the number of heads I'm getting. One toss, number of heads is Bernoulli. 10 tosses, toss number of heads, a count of the number of heads is binomial. Binomial essentially meaning because there are two outcomes that need trials, it's either success or failure, heads or tails. And I'm actually counting, so I'm adding all these up here. So this is the number of successes. X counts the number of successes in n IID, which means independent and identically distributed. Same distribution as every other one, Bernoulli trials. So in this case, X has what we call a binomial distribution. We write the thing in this sense as binom, or you'll find me writing the thing as bin as well. Bin is more common. I don't know why I got binom there, but binom is the function that R uses. The probabilities here are more complicated. If you understand this, fantastic. If you don't worry, ask me afterwards. The mean is NP, makes sense. If I've got success as probability P and I've got n trials, if I've got probability of heads is 0.5, I toss the coin 10 times, I expect half of them to be heads. 10 times 0.5, 5. That's how that works. The variance is more complicated, it's NP times 1 minus P. And essentially what's going on here is, for the Bernoulli, I had my variance was P times 1 minus P. Because I've got n of these, it essentially becomes n times as much in this context here. So it's nice to know these results here, that for a binomial distribution with parameters n and p, I've got the mean is np and the variance is np 1 take p. Assumptions are important. I'm assuming that I've got n independent trials Each trial has two possible outcomes. That's always or mostly okay in these kind of situations. But the more important ones here are going to be independent. Probability of success is fixed throughout. Right? Those two are the important ones. Of course, I'm counting the number of successes here as my binomial distribution. But the ones, whenever I apply a distribution to some particular case, I must make sure, again, the assumptions hold. The two key assumptions here are these. Independent trials, probability is the same for all trials. If I'm looking at, for example, some not so nice examples, as the probability of birth defects. I'm looking at a number of ladies who are about to deliver a child. I'm looking at a number of birth defects in, say, 20 expectant mothers. Now, I could expect that the incidence of a child with some particular issue is independent between the ladies. I can assume that fairly reasonably. But can I assume that the probability is the same for each lady? More difficult, right? More difficult. The two assumptions, independence and constant or fixed probability, are the ones that you'll always question with binomial to justify its application. Now, it might not be independent either. What if I've got 10 ladies there, 20 ladies in my sample so far, 5 indigenous? They might have a higher rate of the possibility of a deformed child. Or let's take a look at something else, miscarriage, for example. But have a higher chance of miscarriage, right? So my model for binomial might not hold here. Be careful when you use models of this kind. You must always look at assumptions. Any questions? Some things we'll pick up over and over again in the course here. I know the first 2 weeks were quite full, but we need that to move along with the course. You need to keep up to date with this because things move rather fast. But if you keep up to date in the first 2 or 3 weeks, you'll find the rest becomes easier. Any questions? All right, great. So much in the lab this week. This first lab is this afternoon or is it tomorrow? This afternoon. Be there, I might drop in. Thank you. See you later on. Next week at least.